Last time we spoke about the Einstein field equations and what the Einstein field equations mean. In this video, we're going to solve the Einstein field equations for the case of a non-rotating spherically symmetric mass to get our Schwarzschild solution. Let me start by stating the Einstein field equations, which consist of the Ricci tensor on the left minus half the Ricci scalar times the metric tensor plus the cosmological constant times the metric tensor. And on the right-hand side, you have your 8 pi g over c to the power 4 times the stress energy momentum tensor t. Of course, for every tensor quantity in this equation, I'm writing the subscripts mu and nu to denote the fact that these are the components of that tensor quantity we're talking about. In the last video, we also discussed two ways of solving the Einstein field equations. The first way is to assume a mass-energy distribution, the tensor t, and solve for the corresponding spacetime geometry, so your metric tensor. The second way is to assume a spacetime geometry and solve for the corresponding mass-energy distribution. In this video, we're going to use the first way and assume a particular mass-energy distribution and solve for g, and that's how we're going to get the Schwarzschild solution. But before we begin solving for the Schwarzschild solution, we need to formulate the problem and put forward our assumptions. The problem we're dealing with is as follows. Suppose I have a static, uncharged, non-rotating spherical mass m with no other sources of mass or energy around it. Let me state the assumptions explicitly. The first is that we're only worried about the space-time geometry outside the spherical mass. So we're only worried about the space-time geometry in the surrounding vacuum. Now, in that surrounding vacuum, there is no mass or energy, meaning that the stress energy momentum tensor is 0. Inside the mass, sure, there's mass and pressure, meaning the stress energy tensor won't be 0, but outside the mass, it will be 0. By the way, making this assumption means that we're going for the exterior Schwarzschild solution. The second assumption we'll make is that there's no vacuum energy. What do I mean by this? Well, it means that for this particular situation, for Schwarzschild geometry, we ignore the accelerated expansion of the universe and set our cosmological constant to 0. The cosmological constant is the quantity in the Einstein field equations that describes vacuum energy, and it's also closely related to dark energy, so we're just going to set that to 0 here. The third assumption we'll make is that the spacetime geometry solution, the metric tensor solution, is Lorentzian. What does that mean? Well, it means that the metric signature, the signs of the diagonal components of the metric tensor g, are -1 for the time component and +1 for the 3 spatial components. Now, why do we make this assumption? Well, if we've got a massive sphere in the middle of our spacetime surface, then very far away from that sphere, we would be in a region of 0 or close to 0 spacetime curvature. So when we get further from the spherical mass, our metric tensor should approach the metric tensor of flat spacetime, of a 0 curvature, 0 gravity spacetime. And what is the metric tensor of flat spacetime? The Minkowski metric. So as we get further from the sphere, the value of the metric tensor gets closer and closer to that of the Minkowski metric. Since the Minkowski metric is represented by this diagonal matrix, with the first element being -1 and the other 3 elements being +1, that means the general metric tensor solution for the Schwarzschild problem should also have similar signs for its diagonal components. And that's why we'll pick this as our default sign convention for really all our metric tensor solutions to the Einstein field equations. Now, you can still have the signs of the diagonal components change, but they would have to change in a smooth, continuous manner, which is what happens at the event horizon for the Schwarzschild solution. But you can't have random patches of the spacetime surface with different signs on the diagonal components of the metric, because that would introduce jump discontinuities which are unphysical. We'll talk about the event horizon later on once we've derived our Schwarzschild solution, so don't worry if you don't know what that is right now. The fourth assumption we'll make is that of spherical symmetry. I'll show you what this means. Let me draw a non-rotating sphere here in the middle, and let me draw a point outside the sphere out here. This point A has a radial coordinate r, an azimuthal angle theta, so the angle from the positive x-axis, and a polar angle phi, so the angle from the positive z-axis. If I draw another point with the same coordinates but a theta angle that's flipped to negative theta, that point is going to be somewhere here. I'll label this point B. I'll draw a third point C as well with the same coordinates as A, but now the polar angle phi is flipped. What spherical symmetry means is that the value of the metric tensor should not change as we go from A to B and as we go from A to C, or even B to C for that matter. And finally, the fifth assumption we'll make is that space-time is static, meaning that the metric tensor components do not depend on time. This makes sense because we're just describing the space-time geometry around a sphere that's just sitting around. It's not moving, it's not going anywhere, so there's no reason for the space-time geometry around that sphere to depend on time. We'll see in a later video that we can somewhat relax this assumption via Birkhoff's theorem, but I'll get to that later. For now, I'll assume a static metric tensor solution. We now have two tasks remaining for the introductory part in deriving the Schwarzschild metric. The first task is to use assumptions 1 and 2 to simplify the Einstein field equations for our specific problem, and the second task is to use assumptions 3 to 5 to come up with a hypothesized metric tensor solution, also known as an ansatz, that will be the general form of the solution to the Einstein field equations for the Schwarzschild problem. Let's start with task 1 by copy-pasting our Einstein field equations here. By assumption 1, the stress-energy tensor on the right is 0, and by assumption 2, the cosmological constant term is 0, so we'll cancel those out and be left with the following for the Einstein field equations. I'll call this equation 1. Let's now multiply both sides by the inverse metric tensor, so g super mu nu, and then sum over mu and nu. When we do that, this is what we get. We haven't put in the summation symbols here because we're using Einstein notation, so indices that are repeated twice are automatically summed over. In this case, they're summed from 0 to 3 because we're working in 4 dimensions. Now this first term on the left is just the Ricci scalar by definition. When you actually multiply the components of the inverse metric tensor with the corresponding components of the Ricci tensor, and then sum all of those components, because the indices are repeated twice, you basically get the trace of the Ricci tensor with respect to g, which is just the Ricci scalar. Meanwhile, the second term on the left, the inverse metric times the metric, is just the Kronecker delta symbol summed over the index mu from 0 to 3. Since the Kronecker delta symbol has the same superscript and subscript, it doesn't just reduce to 1, it becomes 4 because we're basically taking the trace, the sum of diagonal elements of a 4x4 identity matrix. So now when we plug these things in, we get r minus half of 4 times r equals 0, so r minus 2r is 0, which means that the Ricci scalar is just 0. If we now plug this into equation 1, the second term on the left goes away because the Ricci scalar is 0, and so we're left with the Ricci tensor components all being equal to 0. I'll call this equation 2. Now this equation, or more accurately equations, have a special name. They're called the vacuum Einstein field equations. It's not a single equation because you need to equate all the components of the Ricci tensor to 0. It's a system of equations for each Ricci tensor component. So we've completed task 1 and found the simplified Einstein field equations we need to solve to get our Schwarzschild solution. Let's now start with task 2 and develop the ansatz, the educated guess, for our Schwarzschild solution. I'll start by using assumptions 4 and 5 to show that the Schwarzschild metric must be diagonal. We'll suppose that our default time, radial, and angular coordinates are represented by the x super I coordinate system. We'll also suppose that our transformed coordinates, where we go from positive theta to negative theta, are represented by the x super I bar coordinate system, like so. The relationships between all the barred coordinates and the unbarred coordinates are summarized as follows. Now, because the metric tensor is a covariant tensor of rank 2, the transformed component g mu nu bar in the new coordinate system would be related to the unbarred components by the following equation, the following transformation law. Now, if we consider the mu comma 2 component of the transform metric tensor, so the mu is a free index but the 2 is a fixed index representing the theta component, this is what our transformation law becomes, where I just substituted the nu as 2. The indices a and b on the right are being summed over, but the only time these partial derivatives are non-zero is when a and mu represent the same index. The reason for this is our coordinate transformation equations up here. They only relate the barred coordinates to their corresponding unbarred coordinates and not any other coordinates. So x super 1 bar is only related to x super 1 and not to any other coordinate like x super 3, for instance. This means that this first partial derivative is 1, as long as mu isn't also 2, because then it would be negative 1. Meanwhile, the second partial derivative can only be negative 1 if b is 2, otherwise it's 0. So therefore, in terms of the original g sub mu comma 2, the corresponding transform metric tensor component is just the negative of the original, as long as mu isn't 2. But this coordinate transformation, where we just flipped one of the angles, shouldn't actually change that metric tensor component. The metric tensor at the flipped angle should still be the same because of spherical symmetry, so this mu2 component is the same between coordinate transformations, but it's also negative between coordinate transformations, so the only possibility is that this metric tensor component, the g sub mu2, is 0 if mu is not equal to 2. By a similar logic, you could also consider a coordinate transformation where we flip the sign of phi. In that case, as long as mu is in 3, the metric tensor component g sub mu3 is also 0 because of spherical symmetry. And finally, because the metric is static with time by assumption 5, if we consider the coordinate transformation where we flip the sign of t, then as long as mu isn't 0, we can show that the metric tensor component g sub mu0 is also 0 because of the static nature of the problem. Hopefully these last few lines weren't too hard to follow, but if they are, I encourage you to go over the algebra again just in case you're confused, and to ask any questions in the comments if the confusion persists. So anyway, because of these three conclusions, which basically say that the off-diagonal components of the metric are all 0, we can conclude that the only non-zero components are the diagonal components, so the metric is represented by a diagonal matrix. But what do these diagonal components look like? Well, suppose that I'm at a location in space-time with a fixed t and a fixed r coordinate. If my t and r are fixed, then again, because of the spherically symmetric nature of the problem, the line element represented by the metric tensor should be the exact same as the line element of a sphere of a fixed radius. This means that when dr and dt are 0, so t and r are basically fixed, the line element ds squared should equal the following, which is just the line element of a sphere. So the 2,2 component of the Schwarzschild metric is r squared sine squared phi, and the 3,3 component is just r squared. But what about the last two diagonal elements, the 0,0 component and the 1,1 component? Well, again, by the spherical symmetry of the problem, these components are, in general, functions of only r. They don't depend on t because it's a static problem because of assumption 5, and they also don't depend on theta and phi because of spherical symmetry. I've put a negative sign out in front of the time component because of assumption 3, that our space-time surface is Lorentzian. So in conclusion, the most general form for the metric tensor solution to the Einstein field equations satisfying the assumptions required for the Schwarzschild solution is the following. B of r and a of r are functions that we ultimately have to solve for using the simplified vacuum Einstein field equations. But before we solve the vacuum Einstein field equations, let's find a way of how to calculate the Christoffel symbols corresponding to the Schwarzschild ansatz. I'm going to do the slightly less insane thing of showing you an easier way of calculating the Christoffel symbols and giving you the general formulas in the case of a diagonal metric tensor. Diagonal metric tensors are pretty common. They show up all the time in general relativity with the Schwarzschild metric, the Reissner-Nordström metric, the Minkowski metric. They even show up frequently in differential geometry for your classic curvilinear coordinate systems, like spherical coordinates, cylindrical coordinates, polar coordinates, etc. These metric tensors are all diagonal. Their non-diagonal components are all 0. So it makes sense that in order to make your future calculations simpler, we come up with a general formula for the Christoffel symbols corresponding to a diagonal metric tensor. Let's suppose that our metric tensor G with the components G sub ij represents the metric tensor for an n-dimensional space and coordinate system with orthogonal curvilinear coordinates. What does that mean? Well, it means that if the basis vectors for this space and coordinate system are given by E sub I, where I is some free index that can vary from 1 to n, then if I've got orthogonal curvilinear coordinates, that means the dot product of E sub I and E sub j is 0 when I and j are not equal. And because the components of the metric tensor G sub ij are defined as the dot product of E sub I and E sub j, that means the metric tensor is diagonal in orthogonal curvilinear coordinates because all the off-diagonal terms are 0. An example of an orthogonal curvilinear coordinate system is spherical coordinates. From a previous video, I showed that the metric tensor for spherical coordinates is given by the following. You can see that this is a diagonal metric tensor. It's represented by a diagonal matrix. So this basically confirms that spherical coordinates are orthogonal curvilinear coordinates. The off-diagonal terms in the metric are all 0. Anyway, let's suppose G is our diagonal tensor and that we want to find the Christoffel symbols corresponding to G. We'll start by working on the Christoffel symbols of the first kind. Recall that these symbols are given by this formula, where the x super I, x super j, and x super k represent individual coordinates in the x super I coordinate system, with x super 1, x super 2, x super 3, etc. all the way to x super n. We'll work through this problem in parts because there isn't a single general formula for the Christoffel symbols for all possible index combinations. There's different formulae for different index combinations. So we'll start with the first kind Christoffel symbols for a diagonal metric where the ijk indices in the Christoffel symbols are all different. Since these indices are all different, that means g sub jk, g sub ki, and g sub ij are all 0 because they all represent off-diagonal metric tensor components, and our metric tensor only has non-zero diagonal components. To get diagonal components, you need to have the indices equal each other, but here, none of them are equal. And because these three metric tensor components directly show up in the definition of the first kind Christoffel symbol, we can conclude that gamma sub ijk is 0 for the diagonal metric when ij and k are all different. I'll call this equation 1a. The second scenario we'll consider is when the last two indices of the first kind Christoffel symbol, so the j and k, are equal but they're different from I. In that case, g sub ki and g sub ij are 0 because k and j are different from I, so these metric tensor components basically represent off-diagonal components. If that's the case, then my first kind Christoffel symbol would just be reduced to this, and since j and k are equal, we can write this expression with the last two indices both being j, so the first kind Christoffel symbol in this case becomes half of the partial of g sub jj with respect to x super I. Bear in mind that even though it's repeated twice, the index j is not summed over. We're not using Einstein notation for this particular equation. J and I are both free indices. I've called this equation 1b. In addition, since the Christoffel symbol of the first kind is symmetric in the first two indices, we can also simultaneously show that the same formula applies for when the first and last indices, the I and the k, are the same, but the middle index is different. I'll call this equation 1c. The next scenario we'll consider is if the first two indices I and j are equal but different from k. In that case, the metric tensor components g sub jk and g sub ki are 0 because they're off-diagonal components, which means that the first kind Christoffel symbol becomes the following. If I write the index j as I, this is what we'll have for the first kind Christoffel symbol of a diagonal metric if the first two indices are the same. Again, we're not summing over the I is a free index. We're not writing in terms of Einstein notation here. I'm going to call this equation 1d. And lastly, we'll suppose that all three indices I, j, and k are equal. When that happens, all the metric tensor components in the equation for the first kind Christoffel symbol are equal but non-zero, which means that gamma sub ijk becomes the following. And since ij and k are all equal, we can just write them all as the same index I. Again, I is just a free index here. And I'll call this equation 1e. So now we've found the formulas for the first kind Christoffel symbols for a diagonal metric tensor, a metric tensor corresponding to an orthogonal curvilinear coordinate system. Let's work on the second kind Christoffel symbols now. Recall that in terms of the first kind Christoffel symbols, the Christoffel symbols of the second kind are defined as follows. The index r is summed over, and g super ir represents the components of the inverse metric tensor. Note here that I've deliberately chosen to write out the summation symbol instead of leaving it out and using Einstein notation. The reason for this is that I'm not using Einstein notation right now because I'd like to prevent confusion with repeated free indices. So if I'm summing over something, I'll explicitly use the summation symbol, at least for the rest of this video. Now, if the regular metric tensor is diagonal, that means the inverse metric tensor must also be diagonal. This means that the only non-zero components of the inverse metric tensor are the diagonal components, which are just equal to the reciprocal of the corresponding diagonal components of the regular metric tensor. So g super ii is 1 over g sub ii, where I is an index from 1 to n. The off-diagonal components of the inverse metric tensor are all 0. Again, let's consider different index combinations to find the formulas for our second kind Christoffel symbols with a diagonal metric. We'll start with the index combination of I, j, and k, where none of the indices equal each other. If that's the case, the only non-zero component of the inverse metric tensor occurs when r equals I, so all the terms in the summation on the right cancel except when r equals I. When this equality happens, our second kind Christoffel symbol looks like this. But this first kind Christoffel symbol on the right vanishes when the I, j, and k indices aren't equal, which means the second kind Christoffel symbol also vanishes. I'll call this equation 2a. But what if we have the bottom two indices equal? Again, as far as the summation is concerned, every term goes away except when r equals I, because the inverse metric tensor also has its off-diagonal components all equal to 0. So we have this left as our expression. Since we've set the bottom two indices equal in our second kind Christoffel symbol, this means that on the right-hand side of the expression, the first two indices of the first kind Christoffel symbol are equal. But we already have a formula for this in equation 1d. The indices are a bit different in equation 1d, but if we plug in equation 1d with the indices appropriately switched, here's what we get for our second kind Christoffel symbol with the bottom two indices being the same. Note that I've already put in the g sub ii in place of the inverse metric tensor component. I'll call this equation 2b. The next scenario we'll consider is if the I and the j are equal. In that case, the second kind Christoffel symbol becomes the following. Again, we've gotten rid of the summation because the inverse metric tensor is diagonal, so the only component left in the summation is g super ii. Now this time, since I and j are equal, we've got a first kind Christoffel symbol on the right with its first and third indices equal to each other. If we then use equation 1c to plug in that first kind Christoffel symbol, this is what we end up with. I can now move this 1 over g sub ii inside the parentheses and use the chain rule in reverse to write the second kind Christoffel symbol as the following. Note that I've also used a property of the natural log here to move the half inside and convert the argument of the log into a square root. I'll call this equation 2c. Now, since the second kind Christoffel symbol is symmetric in the bottom two indices, the same formula applies to gamma super I sub ki. Again, repeat indices are not summed over here. I'll call this equation 2d. And finally, if all the indices I, j, and k are equal, this is what we end up with for the expression for the second kind Christoffel symbol in terms of the inverse metric tensor components and the first kind Christoffel symbol. If I then plug in the expression I found earlier for gamma sub I, this is what I have. And once more, if I use my chain rule in reverse, this is what I'll get for my gamma super I sub ii, and this will be equation 2e. So there you have it. We found the formulas for the Christoffel symbols of the first and second kind corresponding to a diagonal metric tensor. Let's now apply these formulas to an example. We'll consider a diagonal metric tensor that looks like this. The first diagonal element is some function negative b of r, the second is some other function a of r, while the third and fourth elements are the following. If you've seen my videos on general relativity, you'll notice that this is just our ansatz, our hypothesized solution, or our educated guess for the space-time geometry around a static spherically symmetric mass. So this metric is really just our Schwarzschild metric, the ansatz for our Schwarzschild metric. Now, because we're working with a 4x4 metric tensor, that means we're in a four-dimensional space, and so we have four coordinates needed to describe that space. In this case, the coordinates are t for time, r for the radial coordinate, and theta and phi for the angular coordinates, the angle from the positive x-axis and the angle from the positive z-axis respectively. These coordinates are indexed from 0 to 3 as opposed to 1 to 4. This is just by convention, which assigns 0 or x super 0 to the time coordinate. It's fine if you index from 1 to 4, but just make sure that you're consistent, because a lot of other resources like to index time with 0. In any case, let's calculate a few second-kind Christoffel symbols for this diagonal metric tensor. The first one I'll do is gamma super 0 sub 0, 1. From equation 2c that we derived previously, this symbol would just equal the partial with respect to x super 1, which is just the r coordinate, of the natural log of the square root of the absolute value of negative b of r. If I apply the chain rule to this expression, I get the derivative of b with respect to r, or just b prime divided by 2b. Again, because of the symmetry of the Christoffel symbol in the bottom two indices for the second kind Christoffel symbol, this is exactly also equal to gamma super 0 sub 1, 0. We'll calculate another Christoffel symbol for this metric tensor, gamma super 1 sub 2, 2. Based on the formula we found earlier, equation 2b specifically, this is how we would calculate this Christoffel symbol. Then if we plug in the metric tensor components, here's what we'll end up with. If we take the derivative now with respect to r and simplify, we end up with negative r sine squared phi over a. You can keep going and you can keep calculating the other Christoffel symbols. I won't do all the computations here because they're pretty simple plug-in calculations, but ultimately you only have 13 non-zero Christoffel symbols for the Schwarzschild ansatz. You eliminate a bunch because the metric tensor is diagonal, so automatically your gamma super I sub jk for different ijk is 0. You also eliminate a bunch because only one of your components depends on an angular coordinate, the others just depend on r, so you go from 64 possible symbols of the second kind to just 13. I've stated the other 10 non-zero symbols here for your reference, and I encourage you to go through the calculations yourself based on the general formulas we derived. Let's continue solving for our Schwarzschild metric by computing the Ricci tensor components of that metric. We're then going to use those components to solve the Einstein field equations and end up with the solution for our Schwarzschild metric. Let's begin by recalling 4 things. The first is our Schwarzschild ansatz, our educated guess for the metric tensor solution to the Einstein field equations corresponding to a static, spherically symmetric mass. Note that B and A are exclusively functions of the radial coordinate r. Recall also from our previous video that after using the formulas we derived for the second kind Christoffel symbols corresponding to a diagonal metric tensor, this is what we got for the non-zero Christoffel symbols for the diagonal Schwarzschild ansatz. Note that the 0 index represents the time coordinate, the 1 our radial coordinate, the 2 our theta coordinate, our angle relative to the positive x-axis, and the 3 our phi coordinate, our angle relative to the positive z-axis. The third thing to recall is also from a couple of videos ago that the Einstein field equations corresponding to Schwarzschild geometry are simplified to the Ricci tensor components all equaling 0. These are the vacuum Einstein field equations, meaning no dark energy and no other sources of mass or energy in the space surrounding our spherical mass. I've used I and j as the indices on my Ricci tensor here instead of the conventional mu and nu, but it's still the same idea. The fourth thing to recall is that the Ricci tensor is basically a contraction of the rank 4 Riemann curvature tensor, whose components are calculated using the Christoffel symbols. Now, in terms of those second kind Christoffel symbols, the Ricci tensor components r sub ij are written with the first 2 terms being the derivatives of the Christoffel symbols with respect to the coordinates, and the second 2 terms being written as the difference of the product of the Christoffel symbols. Of course, I've written down this expression in terms of summations. You don't need to write it with summations. You can use Einstein notation to make it a little more concise, but I've used summations here to make things more clear for you. I haven't actually covered the intuitive meaning or even the formal definition of the Riemann curvature tensor or the Ricci tensor yet in my tensor calculus series, but for the purposes of this video, it's sufficient to just know this formula instead of the rigorous meaning and intuition behind the Ricci tensor. Now, just so you guys can follow along more easily and to prevent me from having to scroll up and down repeatedly, I'm going to pin these 4 facts to the left side and to the upper part of my board and just change what I'm doing in the middle so you can easily look at the facts that I've mentioned and reference them throughout the video. So now that we've found our second kind Christoffel symbols for the Schwarzschild ansatz, let's go ahead and calculate the Ricci tensor components. If you brute force your way into calculating all 16 Ricci tensor components, you'll be dealing with an algebraic dumpster fire, but it's a lot simpler than that. The Ricci tensor in this case is also a diagonal tensor, so all the off-diagonal components are identically 0, while the diagonal components are not identically 0. The diagonal components are still supposed to be 0 because they need to satisfy the vacuum Einstein field equations, but they're not identically 0, meaning we won't just get 0 if we calculate them using our Christoffel symbol formula. I'm going to state this fact without proof. If you really want to brute force your way into calculating the off-diagonal components of the Ricci tensor, you can, but for the purposes of finding our Schwarzschild solution, that's not really helpful, so I won't do it here. Let's start by calculating the 0, 0 component of the Ricci tensor. If we plug in I as 0 and j as 0, then this is what I'll have for my expression for the 0, 0 Ricci tensor component based on my formula in fact number 4. But we can actually simplify this significantly. If we look at our Christoffel symbols on the left, the only non-zero term in this first partial derivative occurs when k equals 1. There's no other non-zero Christoffel symbol component like gamma 0, 0, 0 or gamma 2, 0, 0. The next partial derivative term is a partial with respect to t, and there's no t term in any of our Christoffel symbols, so this just goes away. The third term in our r0, 0 equation is only non-zero when k equals 1, but when k equals 1, any value of m applies for the second Christoffel symbol, so we still have to sum over m from 0 to 3 here. And finally, in the fourth term, the only non-zero Christoffel symbol for k equals 0 is m equals 1. Similarly, for the same fourth term, the only non-zero Christoffel symbol for k equals 1 is when m equals 0. The other two values of k just give you a 0 Christoffel symbol. So let's now rewrite our expression for r0, 0 after we've used these simplifications. The first term just reduces to this, the second term is always 0, the third term reduces to this summation over m, and the fourth term reduces to the sum of these two terms. The rest of this is just plugging in the Christoffel symbols and mindlessly simplifying. Now this derivative term is really the derivative with respect to r of b prime over 2a. If we use the quotient rule, we get the derivative of b prime, so b double prime, times the denominator, so 2a, minus the derivative of the denominator times the numerator, divided by the denominator squared, so 4a squared. If we plug in the rest of the terms, this is what we get. Now, if we simplify further by combining terms with a common denominator, here's what we end up with, our simplified expression for the R00 component of the Ricci tensor. Again, capital A and capital B are exclusively functions of the radial coordinate r. Their primes denote derivatives with respect to r. But this Ricci tensor component, just like all the others, has to satisfy the vacuum Einstein field equation, so R00 must equal 0. If we then set this Ricci tensor component to 0, here's what we have. We can now multiply both sides of this equation by the common denominator, 4a squared br. If we do that, we get the following equation corresponding to the 0, 0 component of the Ricci tensor. I'll call this equation 0. The next thing we'll do is calculate the 1, 1 component of the Ricci tensor. If we plug in I equals 1 and j equals 1, this is what our Ricci tensor formula becomes. And let's now make some simplifications. If we look at our Christoffel symbols on the left, the only non-zero term in this first partial derivative occurs when k equals 1. For the other partial derivative term, every term from k equals 0 to 3 is non-zero, so we have to keep everything for this term. For the third term, the only non-zero Christoffel symbol occurs when k equals 1. Again, every Christoffel symbol here from m equals 0 to 3 is non-zero, so we have to keep all of those. For the fourth term, you can simplify it by noting that if k and m are not the same, then the fourth term becomes 0. You can see this if you compare it to the non-zero Christoffel symbols we have available. For instance, if k were 1, then m can only be 1 because there's no second kind Christoffel symbol that's 113 or 112, for instance. Those are 0. So if we now take and apply all these simplifying facts, this is what we get for the R11 Ricci tensor component. These two derivative terms cancel out, by the way. Next, we'll evaluate the derivatives of these Christoffel symbol components with respect to x super 1 or with respect to r. We'll again use the quotient rule for the 0, 1, 0 Christoffel symbol and simple differentiation for the 2, 1, 2 and 3, 1, 3 symbols. We'll then plug in the rest of the symbols to get this expression. And finally, we'll simplify to end up with the following for the R11 component of the Ricci tensor. Just like before, this Ricci tensor component has to satisfy the vacuum Einstein field equations, so R11 must equal 0. If we then set this Ricci tensor component to 0, we can now multiply both sides of this equation by the common denominator 4ab squared r. If we do that, we get the following equation corresponding to this R11 component. I'll call this equation 1. Lastly, let's calculate the 2, 2 component of the Ricci tensor. If we plug in I equals 2 and j equals 2, here's what our Ricci tensor formula becomes, and now let's simplify. The first partial derivative is only non-zero when k is 1 or 3. Meanwhile, the next partial derivative term is always 0 because none of our non-zero second kind Christoffel symbols contains a term in theta, and x super 2 represents the theta coordinate. For the third term of this Ricci tensor component, the k22 Christoffel symbol is only non-zero when k is either 1 or 3. And for the fourth term, the k equals 0 term is always 0. The k equals 1 term is only non-zero when m is 2. The k equals 2 term is only non-zero when m equals 1 or 3. And the k equals 3 term is only non-zero when m equals 2. If we now apply these simplifications, here's what we'll get. We're still left with this summation in the middle. The first term in the summation is non-zero for m going from 0 to 3, so we'll have to fully expand it out. The second term is only non-zero when m equals 2. We'll now plug in our Christoffel symbols. This first term, this partial derivative, is found once again by using the quotient rule, and it turns out to be the following. The second term, this partial derivative in phi, is found by using the product rule on negative sine phi cosine phi to end up with this. We'll then plug in the other Christoffel symbol terms to get the following. We'll cancel some like terms and simplify to finally get this equation for our R22 Ricci tensor component. Again, this has to equal 0 based on the vacuum Einstein field equations. Now the sine squared phi term can't always be 0. This whole equation has to be valid for all locations in the spacetime surrounding the spherical mass, so the only possibility is if the term in the brackets is always 0. We'll then multiply this equation using the term in the brackets by 2a squared b to get the following, and then I'll call this equation 2. So in the end, we've got equations 0, 1, and 2 as our system of nonlinear coupled differential equations that arise from setting the Ricci tensor components to 0 in order to solve the vacuum Einstein field equations to get our Schwarzschild metric. These are really all the equations you need. And you might ask, well, what about the R33 component? Well, if you actually go through the algebra to calculate R33, you find that it's the exact same as R22, except R22 has an additional factor of sine squared phi, so it's kind of redundant. Now that we've got everything in place, let's complete our solution to the Einstein field equations for the static, spherically symmetric mass to end up with our Schwarzschild solution. But let's recap what we've got so far. We've got the ansatz, the educated guess for the Schwarzschild metric under 1. We've got our corresponding non-zero Christoffel symbols under 2. We've got the vacuum Einstein field equations under 3. And under 4, I'm actually going to erase the formula for the Ricci tensor components and instead put down equations 0 to 2 that we derived in the last video. Recall from our previous video that we found these 3 Ricci tensor components corresponding to our Schwarzschild ansatz and set those to 0 to satisfy the vacuum Einstein field equations. The equations corresponding to the Ricci tensor components being 0 we labeled as 0 to 2 for the R00 to R22 components respectively. The R33 component turned out to be redundant because it's the same as R22 except without the sine squared phi. Meanwhile, the off-diagonal Ricci tensor components all become identically 0, so I haven't included them here. So let's now start solving the differential equations given by equations 0 to 2. To start, we'll add equations 0 and 1 because you'll notice that these two equations share a bunch of terms with each other. When we do that, here's what we get after canceling common terms. You'll notice that this term on the left is really just the derivative of the product of a and b. So if this derivative equals 0, then the product of a and b is a constant, which I'll call capital K. How do we find capital K? Well, in Schwarzschild geometry, if we're really far away from the massive object, then our spacetime geometry should approach that of a flat spacetime, of a spacetime with no gravity. So our Schwarzschild metric should approach a Minkowski metric as the r-coordinate approaches infinity. And if we look at our Schwarzschild ansatz, we can see that for our metric to approach a Minkowski metric as r approaches infinity, a and b have to approach 1. So as r approaches infinity, a and b approach 1, which means that the product of a and b, our constant k, must also approach 1. But capital K is a constant in R, so its value should be the same for all values of R, very large, very small, etc. So if we know that K equals 1 as R approaches infinity, we can conclude then that capital K must be 1 to begin with. So A of R times B of R is 1. I'll call this equation 3. Let's now use this fact to solve equation 2. We'll plug A times B equals 1 into equation 2 initially, so we'll get things to simplify to the following. Now since A is just 1 over B from equation 3, that means A prime is just negative B prime over B squared from the chain rule. If we now plug this into our simplified equation 2, here's what we'll get. We'll now multiply both sides by B to end up with the following. We can easily now combine like terms and isolate our B prime or dB by dr. When we do that, we end up with this simple ordinary differential equation. We can now solve this ODE by separation of variables. We move the 1 minus b to the dB side and the dr to the r side. We then integrate both sides to get the negative of the natural log of 1 minus b. There's a negative out front because the b has a negative sign, so we need to take that out. On the right, we get the natural log of r plus some constant I'll call capital K1. We'll then exponentiate both sides to get 1 over 1 minus b on the left, because when you take the negative inside the natural log, you get a power of negative 1 on your 1 minus b. On the right, you get the exponential of k1, which is another constant that I'll call k2, times the exponential of ln r, which is just r. So if we do some algebra and isolate the b, we get 1 minus 1 over k2 times r. Now 1 over k2 can be another constant, which I'll call r sub s, so I have 1 minus rs over r as the solution for b of r. The reason I've called the constant r sub s is that b must be dimensionless as a component in this metric tensor, so the r sub s should have units of distance just like the r coordinate in order to give us a dimensionless quantity. Now since a is 1 over b, that means a is just the inverse of all this, so 1 over 1 minus rs over r. We're almost done because now we just have to find the value of this integration constant rs. This is a bit tricky because there's no initial or boundary conditions we can explicitly plug in to get our rs. We have to use some principles of physics, particularly the limit of classical physics, to get our value for rs. Let's get started with finding rs by bringing back our geodesic equation, which I'll write over here. I derived this equation in one of my videos on tensor calculus, so check that out if you haven't already. Recall that p is a free index, which varies from 0 to 3 in this case, and I and j are dummy indices, which are being summed over from 0 to 3. So the geodesic equation is really a system of 4 differential equations, one for each coordinate in our spacetime. If you solve these equations, you'll be able to find the paths, or the world lines, or the geodesics that test particles would take in that particular spacetime geometry that's determined by these Christoffel symbols. Now, S, if you remember, is the arc length parameter. This is the form of the geodesic equation that we get if we parameterize our world line with respect to arc length. But if you remember from one of my videos on special relativity, you can write the proper time tau directly in terms of the arc length of a time-like world line via this equation. Of course, we expect any particle to locally follow a time-like world line, so in terms of the arc length, the proper time the particle experiences is directly related to the arc length, aka the space-time interval with an additional factor of c, the speed of light in vacuum, in the denominator. Recall also that for a time-like world line, s squared is negative, so tau obviously becomes positive. It's not imaginary. We can then rewrite this expression for tau as the absolute value of s, or the magnitude of s over c. The derivative of tau with respect to s is then just 1 over c. That's because we're only considering positive proper times. So if we use the chain rule, we can write the derivative of some coordinate x super k with respect to s as the derivative of x super k with respect to the proper time tau times the derivative of tau with respect to s. But we know d tau by ds is just 1 over c, so dx super k by ds simplifies to this. When we take the second derivative of x super k with respect to s, we get another factor of d tau by ds. So now the second derivative of x super k in s is its second derivative in tau times 1 over c squared. If we plug these expressions in for the first and second derivatives into our geodesic equation, we get the exact same equation, but this time with a factor of 1 over c squared out front, and also now we're differentiating with respect to tau. We can easily cancel out this factor of 1 over c squared and get a more polished geodesic equation, but now in terms of proper time instead of the arc length parameter. So this makes things pretty convenient. Anyway, let's use this geodesic equation in proper time and look at the coordinate corresponding to p equals 1, which in this case is the radial coordinate r. So we basically replace the x super p, or the x super 1, by r. If we isolate the second tau derivative in r from the geodesic equation, this is what we have. Let's now recall something else from special relativity, the 4 velocity. By definition, the 4 velocity u is the proper time derivative of the 4 displacement x. So these tau derivatives of x super I and x super j are really just the 4 velocity components of our test particle, so u super I and u super j. You'll recall that the u super 0 component, the time component of the 4 velocity, involves the speed of light c, and the spatial components of u involve the spatial velocity of the particle v, so the u1, u2, and u3. This is now where we start to make our assumptions. We'll assume that the speed of light is very, very large compared to the spatial velocity of our particle. So we're going in the classical Galilean relativity limit instead of the Lorentzian c is a finite number limit. So that means on the right-hand side, the dominant term in the summation of the 4 velocity components over I and j is u super 0 whole squared. Because the spatial velocity of the particle is so small, every other term involving the components u super 1, 2, or 3 vanishes in comparison to u super 0 whole squared. That means the only Christoffel symbol we need to worry about for our radial acceleration on the left is gamma super 1 sub 0, 0. We can plug in the Christoffel symbol to get the following equation. Now, if we substitute 1 over a as b and b prime as negative rs over r squared, this is what we get for our second t derivative in r. Additionally, when c is much larger than the spatial velocity, the proper time tau just becomes the regular time coordinate t, so our geodesic equation in r now gets changed to a second derivative of r with respect to t instead of just tau. Let's now make our second assumption that our gravitational field is weak. What this means is that the metric tensor corresponding to our gravitational field can be approximated as the Minkowski metric plus a small perturbation h from that Minkowski metric. This h is very small compared to eta. So in the weak field limit, the b of r component approximately just becomes 1, meaning that our radial acceleration turns into the following. I'll call this equation 4. Additionally, because we're assuming a weak gravitational field, we can use the physics of Newtonian gravity to write an equation for our acceleration in r. From Newton's second law and Newton's law of universal gravitation, the acceleration, after canceling out the small mass m of the test particle, is just g times capital M over r squared. If I plug this into equation 4, I end up with the following. If I then isolate my r sub s, I find that r sub s is 2gm over c squared, where again capital M is the mass of our massive spherical object generating the Schwarzschild geometry. So finally, after all this hard work, we've derived the Schwarzschild metric, the metric of the four-dimensional space-time surrounding a static, spherically symmetric mass, which I will write here as the following. The constant r sub s, the 2gm over c squared, by the way, has a special name. It's called the Schwarzschild radius. Sometimes you'll see the metric written in the form of the line element ds squared, or the spacetime interval ds squared, which you use to calculate distances in spacetime. The Schwarzschild metric would then be incorporated into this line element as follows. Now, this ds squared equation is sometimes also called the Schwarzschild metric, but in reality, the metric refers to the metric tensor given by G. The ds squared is the line element. Anyway, that should do it for this video. In the next lesson, we're going to discuss some physics behind the Schwarzschild metric, including the Schwarzschild black hole. I'd like to thank the following patrons for their support, and if you enjoyed the lesson, feel free to like and subscribe. This is the Faculty of Khan, signing out.